topic questions and then move on to rehashing your enzyme inhibition. Yeah. About what? Catalyze rate. Huh? No. All right. So, question is, when we talk about catalyzed rate, are we talking about K2? Right? So this goes back if I. So is this what you're talking about here? Catalyzed rate. Okay. So what we're looking at here is two separate things. Okay? We're starting with some substrate, and this leads to some product. Okay? This obviously is going to have an equilibrium with a forward rate constant Kf and a reverse rate constant K. Right? Now, what we're looking at here, okay, is what? What does it say at the top? K what? Uncatalyzed Kf, right? So that is simply referring to, if we have this system, okay, this on its own, this Kf is this K uncatalyzed that we see there, right? Easy enough, everyone knows about rate constants, hopefully. Okay, so what are we talking about when we say K catalyzed rate? That is simply saying that now, if we take this system and add the enzyme, we get product plus enzyme. Okay, now we've seen this before, right? We've seen this before when we derived the Michaelis-Menten equation. The only thing that we've omitted here is the formation of the enzyme substrate complex, right? And if we look at this as a normal chemical reaction, well, of course, we can cancel out the enzyme because they appear on both sides of the yields, right? So we can cancel that out. Where we're left with is over here. However, when we do have the enzyme, now we have a K forward, of course, and a K reverse. Okay? In this instance, this K forward is equal to the K cap, right? So this is the macro observation. What is the rate constant of the forward reaction in the presence of an enzyme? And this is not necessarily K cap in terms of like the turnover number for K2, right? That's a separate thing because in that case, what we're looking at is the entire picture. Right? In this case, what do we have? K1, K minus 1, K2, K minus 2. We're ignoring K minus 2, so we get rid of that. Right? Now, what is the velocity of this reaction? K cat times ES. Right? Now, in most cases, well, first, let's define K cat. So remember, what is K cat? Right? K cat is the turnover number, and it is equal to the rate limiting rate constant. In other words, K cat is equal to the smallest of K1, K minus 1, or K2, right? So K cat isn't, you can't put it somewhere specifically, it's just equal to the rate limiting rate constant. Now, as it happens, most of the time, K cat is K2, right? So in that chart at the beginning, it's not K2, it's K cat. Most of those are probably K2. We don't know for sure, just given from that information. K cat is a special rate constant, simply equal to the rate limiting rate constant of all the relevant rate constants in the Michaelis-Menten scheme, right? So that was a good question. So when we look at that, okay, that again, slide 1, where we look at the enhancement rates, what we're really comparing is what's the ratio of the catalyzed rate constant, K cat, over the uncatalyzed rate constant, which is Kf for the uncatalyzed reaction. In other words, how many times enhanced is it, right? So we can think of, right, the velocity here for this reaction is V equals Kf times S, whereas here the velocity is K cat times ES, right? Well, now things get a little bit more nebulous, right? So we can say, what's the ratio of this velocity to this velocity? Right? What's the ratio of this velocity to this velocity? Well, let's say K cat times ES over K forward, or K uncat times S, right? So here, we have a bit of a problem, right? What if we say, for any given substrate concentration, we'll have the same ES, this will be constant, right? So we can ignore that. And we say that now, the rate enhancement is simply equal to the ratio of K cat over the uncatalyzed K forward. Good? All right, let's move on. What else? What else isn't clear? I know I had a lot of questions about chapter 5. And I know specifically some people emailed me about chapter 5, so I know there are questions. Yeah.
I was wondering if you could go over questions.
The homework questions. Okay, sure. Let's do that. Which homework question?
Number 6, I think it was like the hydrolysis of pyrophosphate to orthophosphate.
Alright, let's see if I can figure this out. Hydrolysis of pyrophosphate, pyrophosphate. Alright, you don't remember the number?
I think it was 6.
Let's shoot for 6.
Yeah, that's
This one?
yeah, that's the one.
Alright, so why don't you walk us through then what you've tried? So how do we start this problem? Right? Everyone take a second to read it. Assume that you have a solution 0.1 molar G6P to the solution add the enzyme phosphoglucosamidase. We're going to see this in chapter 16. Catalyze the reaction G6P to G1B.
So first I had the delta G formula where like RT times ln times the K equilibrium. Then I solved for G1P over G6P using that formula.
Okay, so what should I write down here first?
The formula.
What formula?
Delta G prime is equal to minus RT ln K equilibrium.
Alright, let's see if this makes sense. I'm sorry, I have to keep walking back. Alright, the standard free energy change for this reaction is 7.5 kilojoules per mole. What is the final concentration of glucose 6-phosphate? Alright, so we know that the standard free energy change is 7.5 kilojoules per mole. Is that right? Is that what it says? 7.5? Okay. This is equal to negative R, which is 0.008345 kilojoules per mole Kelvin times temperature, right? Does it give us the temperature? Does it give us the temperature? Why? Well, it's not. It is 298, but it's not because it's at equilibrium. Standard conditions, exactly, right? It's 25 degrees Celsius, 298 Kelvin times ln K prime Q. So K prime EQ equals E to the negative 7.5 over 0.008345 times 298. Right? So what does that K prime EQ come out to? right? Is this what we're looking for? Now, what is it asking for? It's asking for the final concentration of glucose 6-phosphate, right? Right, so the final concentration of glucose 6-phosphate. How do we figure this out? Well, we know that this must be what? Exactly, G1P over G6P. So we know that the ratio between G1P and G6P is 0.05, all right? But we have a problem in that now we have two variables. So what do we need when we have an equation that's got two variables? A system of equations, exactly. So we need a second equation that relates G1P to G6P in another way. What is another way that G1P and G6P are related? They both should add up to 0.1 molar, exactly. So we also know then that G1P plus G6P equals 0.1 molar, right? So we can say then that G1P equals 0.1 molar minus G6P. So we can plug that in here and say 0.1 minus G6P over G6P equals 0.05. So now we can solve for glucose 6-phosphate. This case comes out to 0.095 molar. So the concentration at equilibrium is 0.095 molar of glucose 6-phosphate. Now, again, when we're doing these types of calculations, it's always important to sanity check yourself, right? Because it's very easy to mix up a fraction or miss a negative sign, right? So let's start from the beginning. The delta G naught prime is positive 7.5 kilojoules per mole. Does that mean that the reaction went forward or backward? Right, did it go forward? No, right? So, what do we expect the K prime EQ to be? Are we going to have more reactant or are we going to have more product? We're going to have more reactant, right? So should K prime EQ be greater than 1 or less than 1? Less than 1, right? And is it? Yeah, K prime EQ is 0.05. Means that we have more product, so we have more denominator than we do we have more substrate rather, the denominator, than we do product, the numerator, right? So this makes sense of what we're saying. So now let's get all the way to the end here. We started with 0.1 molar, and at equilibrium we have 0.095 molar of glucose 6-phosphate. Does that make sense? Well, most of it is still left over. Right? Most of it is still there, 0.095 versus the 0.1 that we started with. We still have most of the glucose 6-phosphate that we started with, which we expected because the reaction didn't proceed forward. Now, what is the final concentration of glucose 1-phosphate? Well, that's simply just 0.1 minus 0.095, right? So we're left with 0.0045. We have to remember our sig figs for the homework. I could not give one shit about sig figs. Okay, so don't worry about that. 0.05 is close. Okay, the reaction procedure is written, right? You know, of course, under what cellular conditions could you produce glucose 1-phosphate at a high rate? Right? Of course, you don't know the answer because it's on the screen, but why is it the answer? How could we force this reaction to go forward? Right. So Le Chatelier's principle, you know, everybody remembers. We have some reaction at equilibrium, or some reaction with a specific rate constant. If we add more product, or rather substrate, we can force the reaction forward. If we remove product, we can also shove the reaction forward, right? And and we can show this mathematically. Remember, delta G, the actual change in free energy, is equal to delta G naught prime plus RT ln Q, which is in this case B over A, or glucose 1-phosphate over glucose 6-phosphate. So if initially, right, we make sure that our ratio here is high, or rather low, right? So we have little b and a lot of A. This will push the reaction forward. It will make the actual change in free energy negative, right? So this is how unfavorable reactions in the body are forced to go forward. There's a very important reaction in glycolysis, catalyzed by triose phosphate isomerase. This catalyzes the conversion of a sugar called dihydroxy acetone phosphate to glyceraldehyde prephosphate, right? The delta G for this reaction is also, or the delta G naught prime for this reaction is also about 7 or 8, let's call it 7.5 kilojoules per mole positive. So this reaction doesn't proceed forward. But this step is critical in order to get all the way through glycolysis. We have to convert it. We'll see, we'll have to convert dihydroxy acetone phosphate into glyceraldehyde prephosphate. And so, how does the body do this? Well, we already see through Le Chatelier's principle and the calculation of the actual change in free energy, we can increase the amount of DHAP or decrease the amount of glyceraldehyde prephosphate. This will push the reaction forward, making the actual change in free energy be negative so that the reaction does proceed, which we need it to. So how does the body do this? Well, this is the whole concept of what a pathway is, right? So when we think about a pathway is just a series of related reactions. So we have A yields B is the first reaction in a pathway. The second reaction in the pathway is B yields C, and the third would be C yields D, right? Now we can do something interesting here. First, we can add up all these reactions and cancel out what appears on both sides. So B would cancel out because it's made and then used. C cancels out because it's made and then used. So the balanced reaction is really just A yields D, right? But this intermediate here, right? If this has got, again, let's say that this is a reaction here, right? Well, this is getting a steady feed of reactant from step 1, right? So we're getting a lot of B from step 1. So this increases. At the same time, C is being used up by step 3. So we keep this low. This pushes the reaction forward, right? This is why pathways work. They help to aid some unfavorable reaction to proceed forward. A lot of the reactions in metabolism and for life to exist in general are unfavorable. All right.
I just want to make sure I'm correct with the numbers. Shouldn't G be 0.0005
Point 0.1.095 should be 0.005 or 0.0045. 0.1 minus 0.095 is 0.005. Yeah. The decimal point is the decimal point is going to be in the same place. If we do come back up here, right? We now know that glucose 6-phosphate is 0.095, right? Then what is G1B? Well, that's 0.1 minus 0.095. It's 0.005.
Yeah, why is it 0.45? Because even with 6 bits, then it'd be 0.0050.
Because this 0.095 is rounded. Right, so if you round to 0.0045, it's still 0.05. But that 0.095, for the sake of this, is rounded. Alright, this is gonna be hard to read. Okay. Alright, start from the beginning. So what do we have? We've got hydrolysis pyrophosphate to orthophosphate. What is the reaction? Okay, so we have what? PPI, that's pyrophosphate, plus H2O, yields 2 orthophosphates. This is the reaction that we're talking about here. Okay? The hydrolytic reaction is catalyzed by blah, 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 has a mass of 120 kilodaltons. All right, and 6 acrocytes, is that right? Six subunits each with an acrocyte. For this enzyme, the unit of activity is defined as the amount of enzyme that hydrolyzes 10 micromoles in 15 minutes. Holy shit. All right. 10 micromole per 15 minutes. Okay, that's 1 unit. Alright. What is it? Sorry, it's taking a while to get on the board. There's standard conditions of purified enzyme as a Bmax of 2800 units per milligram of enzyme. Okay. Bmax is 2800 units per milligram. Okay. Have we got everything? How many micromoles of substrate are hydrolyzed by this? Alright, whatever. Alright, so first let's start off here. We haven't seen this before, right? We haven't seen Vmax be defined as this, or given us this before. So they're saying that Vmax is 2800 units per milligram of, in this case, pyrophosphate, or pyrophosphate. So why are they giving it this way? Right? Why are they telling us that Vmax is 2800 units per milligram? You know, a unit is 10 micromole per 15 minutes. So why are they telling us per milligram of pyrophosphate? We haven't seen that before. So what's that per milligram? What do we know about Vmax? What formula defines Vmax? Let's start there. Vmax equals what? How is Vmax defined? K cat times what? Yes. Very close. This is not Vmax. What is that? It is a velocity, but what is it? V naught. What is Vmax? It does involve K cat, but not ES. It involves what? V total, right? Okay. Alright. Times E total. Now, E total is really just how much enzyme we add, right? So we can have different Vmax values if we add more enzyme. The higher the concentration of enzyme, the higher the Vmax will be. And that's what it's telling us over here. For every milligram of pyrophosphatase that we add, we increase Vmax by 2800 units. And 1 unit is 10 micromole per 15 minutes, which of course is a velocity, right? So if we have 1 milligram of pyrophosphatase, our V naught is 10 micromole per 15 minutes, or that times 2800, whatever that is, right? Okay, so question is, how many micromoles of substrate are hydrolyzed per second per milligram of enzyme? And such a concentration is much greater than Km. In other words, what is the Vmax of the catalyzed reaction? Right, so we know again, Vmax is 2800 units per milligram. How many micromoles per what? Somebody please read it for me, let's take a walk.
Micromoles of substrate are hydrolyzed
Per second?
per second
Per milligram of pyrophosphate. Right, so what type of problem is this? This is a very simple type of problem. It doesn't even have anything to do with biochemistry. It's just unit conversion, right? It's just unit conversion. So, Vmax is 2800 units per milligram, right? So we already have milligram down here, right? So we don't have to worry about that. Times 1 unit is equal to 10 micromole per 15 minutes, right? So let's just move this down here. So we can say 15 minutes times 1 unit is equal to 10 micromole. Of course, what do we need? We need micromoles per second. So 1 minute is 60 seconds. So this leaves us with what? Micromoles. No, this doesn't cancel out. Minutes cancel out. Units cancel out. What's this leave us with? This leaves us with micromoles per second per milligram. Right? So 2800, 28,000 divided by 60 divided by 15, whatever that comes out to be. Right? So let's see. 2800, 20,000 divided by 15 divided by 60. So that's 31.